All right. We're live for ABNA Code 2024, day 6. And we have 47 minutes to go. Plenty of time to work on day 6 of a previous year. So I think we'll get right into that. Day 5 I was pretty satisfied with. I might have updated a little bit after the last stream. The difference between ANDS 1 and ANDS 2 is just this line here. So we map and we sort it by using the dependencies to implement less than compare function. Pretty easy, makes for a quick delta. Okay, so day 6, 2018. Let me see, we'll make a file for that. And, oh, okay, gotta download that input. Um, 2018, number 6. All right. And I don't know what the input actually is. Okay. It's a list of coordinates. Okay, so we can just parse that into points. Please specify new target coordinates. Device produces a list of coordinates, which is my puzzle input. Okay. If they're dangerous, maybe you can minimize the danger by finding a coordinate that gives the largest distance from the other points. Okay. So these coordinates might be dangerous. We're trying to avoid them using only the Manhattan distance. Determine the area around each coordinate. Area around each coordinate by counting the number of integers that are closest to that coordinate. I'm not sure I get that. Your goal is to find the largest area that isn't infinite. Okay, so for here, oh, so we look for an area around it that has no other coordinates. So we can have an area surrounding this, and we could keep growing it until some other coordinate shows up. Oh, okay. So this problem is perfect for me because I have an area method that can already grow and shrink. I have point classes, or an area class rather. Yeah, so import AOC dot point and area. And points, how does it know? How does it know what the input looks like? Is it looking into the rest of my repo? I mean, okay, whatever, that's correct code. And let's make this a set. And then for each of these, now we want to avoid infinite. Could we possibly get infinite? Sure, well, no, because unless the input only has 1 point, there can't be an infinite. And let's make sure I'm understanding this properly. So we use partial of the grid is infinite. Yeah, my area class handles infinite really well because it defines an area in terms of just a couple of ranges of points. I'm not going to use an actual grid here, just a set of points. Each location's closest coordinate can be determined, shown here. Oh, hold on. I think I am misunderstanding it. So for each location, we don't do a square around here, but for each location, we have to find a point that is closest to it. So some of them can be tied, like this, I suppose. And so how do we avoid the infinite? The area coordinates A, B, C, and F are infinite. Right, okay, because it will keep on going around. Okay. So basically, if an area, if a territory for one of these coordinates has an edge, a border piece of the area, then it's infinite. And A, B, C, F are infinite, and then D and E are not. And I suppose we might have to do more than just a bounding box of these. Had we done the bounding box? Like I could imagine some setup where the end of each territory is here. But surely the end of each territory would never be outside of the bounding box, right? So we could see if it tries to expand outside the bounding box. Right? If the bounding box has things on it, so nothing else can be. Do I have to draw this out? Okay, let's say you had 4 corners that make the bounding box, and you had like a point here. And that's going to be close to a bunch of stuff that's outside the bounding box. So we need to do padding on a bounding box. That would fill out where the 4 corners of that padding bounding box might reach. And at that point, it should be stabilized. Okay. So Val, let's do bounding. Val bounding equals area dot bounding for that set of points. And then we're going to expand. So Val A is that. And we can just take the higher of width and height. And I think we can just tag that on. We don't need to think about like dividing over 2 or whatever. A dot width max A dot height. So this is what we'll call padding. And what we return is A dot expand by padding. Yeah. Okay. And now for each point, at each point in there, we do a search for one of the, what do we call these coordinates? Let's call them points to distinguish them from just generic points. Or let's call them chords rather. Okay, so we partition, we can just do kind of a flood fill. Well, we're doing Manhattan distance. So we can just continue growing an area around a point and checking if that contains any of the chords. So def nearest chord to a point. And I don't think we need to do this. And yeah, I'll say option because there might be none if it's tied. So we'll do the circles around. What do we call that? I'm gonna call them circles. Surrounding. Okay, they are areas. We'll call them areas. So starting with, we're gonna do like an iterate. Iterator dot iterate, and then we have an area around bounding for that point. Yeah, the bounding area for that point, which will be of size 1, 1. Okay, so that's the start. And at each step, we're just gonna expand by 1. Okay. Take while contains bounding. I don't know why they're doing that. That's not good. So now that we have our areas, we're gonna drop while that's empty. Areas that drop while it doesn't contain any other chords. So we could do chords for all order doesn't. Okay, yeah. For all the chords, it's not contained. Now let's say chords, there doesn't exist a chord such that a dot contains that point. Okay. And then val closest. We'll call this closest. These are close candidates. So dot next. Or no. This is not the closest. This is an area. So this is a hit box. I don't know. It's the area that gets hit. So we'll say hit area. And then now we do an option. So option. Actually, we're gonna take the hit area and we're gonna filter those points. Or rather, we're gonna take our chords. Chords that filter hit area dot contains candidates, and then option dot when candidates size equals 1, we do candidates dot head. There we go. There we go. I don't even feel the need to test this. It feels famous last words every time. Exists. Okay. Great. So we can get the nearest chord, and then we'll use bounding. Yeah, so we're gonna do the nearest chord for all the points in bounding. Bounding dot points iterator dot filter not one of the chords itself. Wait, does that count as part of the area size? Yeah, I don't think we need to filter. I'll leave that as a comment just in case we change our mind. So map nearest chord. And I guess that could be a flat map. And let's see, at this point, wait, give me just a second. I need to check my stream health. We're fine. Okay. So flat map nearest chord, and then at this point we just group them. So group by identity. Or do we want to do a group map? Because we want counts for each of these. Yeah, according to the chord they are closest to. And what is... Oh, we just want the size of the largest area. So we can group by identity. And then, yeah, get the size of each of those groups. And then max. And we don't need to do the view.map values. We can just do values. So values. That map. That size. Evans. Welcome. Can I explain my approach? Yes, I can explain. I don't know if you're caught with a problem. I'll briefly go over for everyone else. So list of coordinates here. And for everything in the grid, which is infinite, we have to figure out which coordinate it is closest to. So here it's showing like lowercase, so forth. And now these ones that are on the corner, the area of A's is going to be infinite. So we don't care about that one, but we want the largest of these that is finite. Oh, yes, I need to filter the finite bit. So my approach here is just to take take a bounding box of all of our coordinates, expand that a bit because we have to expand a little bit to see that something's actually infinite. So expand that a bit. And then for every point within that, search which coordinate is closest. So here's that big bounding box. And here's our nearest coordinate. Basically, we take an area that starts at that point, and then we expand it. We keep growing it until that area contains one of the coordinates. And if it only contains one coordinate, then we know that there is a nearest. Otherwise, we know that there is no nearest, and you get one of these period cases. All right, so we group this by identity, get the values, map size. We don't map size yet. So for each of these values, we gotta do a filter and make sure it's finite. So what are we doing here? We have, I don't know, a territory point. So this is a list of points. This is a list of points, P's. So we should make sure that none of these points. Yeah, great, thanks. We should make sure that none of these points are on the border on our extra large bounding area, the border of that. So P's dot for all. Bounding dot contains, not quite bounding dot contains. So we have bounding dot. I think I had a way to get the list of the borders in my area. So bounding dot. Nope. What is bounding? Bounding's an area, right? Okay. Border. Okay, yeah, we have each border, and those are lines, and I think our lines have a dot contains method as well that works over points. No, we just, okay. To do contains method for efficiency in the future. In the meantime, we have our expand. I think I want to have a shrink method. Def expand. Because I'm just going to check if it's inside the border, but not inside one that's shrunk by 1. Oh, I can just expand by -1. Okay. We don't need to write a method right now. Okay, so p is dot for all p. Val inner equals bounding dot shrink. We don't have shrink. Nice try, Copilot. I appreciate it. But bounding dot expand by -1. And we want to make sure that for all these p's, they're not on there. They're not. Yeah, so inner dot contains p and not outer, or rather bounding, that contains p. And if that's true for all the p's, then this set passes. And then now at this point, we can map. Marcus, good morning. I'm doing a problem right now, day 6 from 2018, that I'm finding very fun because my little standard library of points and areas is very well suited for it. So we have a bunch of coordinates, and in this grid, we're looking for each of these points in the grid, we're looking for the closest coordinate and determining the largest area, like the largest territory. That is not infinite. Yes, I'll be glad to explain as I go. I hope I'm doing that. If something is confusing, please feel free to stop me. But here at this point, yeah, we're assigning a territory to everything using this nearest coordinate. Then we're grouping them up, and then now we're filtering in these. So this is checking that a group of points is not infinite. In fact, I might make this a helper method. And then now that we have that, we are getting the size of each of these groups. And then we just get the max, and that should be ans 1. And after fixing some errors here, group by is not member of iterator. Okay, so let's do like a 2 list here. And okay, not the most efficient, but we can think about that. I have tools in place to make this more efficient if necessary. I just played Santa and put candies in my son's shoes for Nicholas. Oh, nice, nice. How old's your son? Oh, okay, we hit a timeout. Okay, fine. What is slow here? We did kind of decide to just look at everything in the bounding iterator, in the bounding box. But for one, maybe we don't really need to do that. So bounding dot size. Ooh, okay, yeah. And for each of those, what I should be doing is a flood fill, a simultaneous flood fill. Well, no, not quite a flood fill. simultaneous floodfill of sorts from each of these coordinates. That would be more efficient because for each of these, we keep searching larger and larger. Or, I mean, if we did a binary search on this, he is 5. Might be the last year he believes the story. Oh no. Well, I hope he has fun, has a good Christmas. Okay. Um, this is still useful to me in that I can use it to test other implementations that are more efficient. So let's do an example input. Can you explain to me what expand does here? Oh, okay. Yes. So I have a custom area class here. Um, so this area class is meant for working with grids. Sometimes with grids, instead of doing like a 2D array, I will do a map or a set of points. And when I do that kind of thing, it's accompanied by an area representing a grid kind of abstractly. So an area is basically composed of two ranges. So the range of, this might be 1 to 10, and this might be like also 1 to 10 for like a square that would be 10 by 10, right? So because that's so the ranges are infinite are efficient for like a one-dimensional sequence. And I can do stuff like this, left, right, top, whatnot. Yeah, very handy util class. I'm happy with this. This has helped me a lot in the past. I have a contains method here that checks very efficiently if a point is contained in there. I mean, like that's easy to do efficiently. And then like what is adjacent to a point. And now my expand does is it grows the area by n in each direction. So I basically copy it, but with a new range, and we take the left side minus n to the right side plus n. Similarly with top and bottom, so we get a larger range. I don't know. We have a transpose. We can move it around, and we can iterate over the points that would be contained in there. And a convenience method for printing the whole array, which in this case, I don't think we can print because apparently this is large. I didn't expect that we'd have such large things on day 6. Oh, and then I can take intersections of two arrays, of two areas. This comes in really handy. Or I could diff an area from like an area from another area to get like a list of the areas that were remaining after removing that. Similar with union. So these areas kind of function like sets. You can intersect, diff, and union. So yeah, it's like a grid class in the abstract where this is really good for like sparse grids, for large sparse grids where, you know, a 2D array is not feasible. And yeah, I use this in there as well. So given a list of points, I can create the area that bounds that. Yeah, when I find time, I can show you an example. Also, let's see, in my GitHub, I'll just pull this up. So there is, I have a list of tests for my point class somewhere in the repo, but there's also um, 2021. There's a problem that uses this. I believe it's like 19 or 20. One of these uses the area to great effect. Uh, 20 is one of them. I think 21 as well. So one of these, I'm looking for. Oh, there was this really cool problem that had basically three-dimensional cubes that you had to take the intersections of, and I did a similar thing in there. But for now, like here's some example code that uses that, and I'll just drop that for you to take a peek at. And let's go back to trying to make this more efficient. Um, oh, and you know what? Here, I can do a simple demo of stuff in my repo here. So we can take an area 1 to 10 and then 1 to 10. And we'll take two areas. So let's make a smaller one. Or you know what? We'll just take 1 to 5 and then we'll expand that as an example. So first we'll take a dot show or print draw. And for every point, I'm just going to draw a dot. So that gives us this string here. You can see that 5 by 5. Or hold on. What is, yeah. And then now if we were to do a dot expand by 10 and draw that, now we have a larger. And we could do things like our draw function could be, if it's in the chords, then something else. So if chords P, then like question mark, else that. Whoops, missed it then. Okay. And in this case, there are none, but maybe if we expand it quite a bit, let's expand 100. I guess there are not any within here. I don't know what my coordinates are, but you get the idea. Thanks. Yeah, I've I've basically sort of had a version of area for 3 years now that I kind of iterate with. Whenever it's helpful, I add more methods to it. A grid problem would be nice. Okay, so my initial approach was to take each of the points within and check. And I do think that was misguided and that's inefficient. Maybe I can salvage this somewhat. Maybe not so many points. Like, what if we just took this divided by 2? Like, if I can sort of brute force this and get an answer, I would just put it in now because we are running low on time. I think dividing it by 2 is fair. And no, that's almost certainly going to time out. So it might turn out that my nearest chord isn't as useful. Okay, even now, our bounding size is 300, and then we're doing kind of an expensive search. The search itself for the nearest chord could be more efficient, significantly more efficient, actually, because what we're doing is checking this, generating all these areas. We could just do the distance between all the other points. So basically take chords, map You think you need to get good in coding some more? How to practice? Um, Honestly, I would read code and write code. So AOC is great for this because so many people are solving the same problem, and you can see different ways of solving it, and read all the solutions and learn all the tricks you see there, and then write some code yourself. Do AOC. Okay, so why didn't I do this from the start? So to find the nearest coordinate, we just take all the chords and then take the Manhattan distance. Dot dist to our point P. Okay. Let's see. And then actually we have to keep that coordinate. So we're going to do dot map C to P dot Manhattan to C. And then min by option 2 sure dot map 1. 1 being the left side of the chord and 2 being the distance. It's not Manhattan, it's dist. Copilot is snooze on me. Okay, this should be significantly more efficient. Yeah, this was a silly attempt here. I think I just wanted to use my expand function more. Okay, well, this is good. In that it is not running infinitely. Okay, empty.max. Okay, we bit ourselves. Oh, here? That's the only place we're doing .max. All right, so let's take this step by step. So, group by identity. Okay, let's call this whole bit here the territory map. So val territory map equals this bit here. So you take the bounding, points iterator, flat map, to list and group by identity. Keep this commented for now. And let's see what that looks like. Oh, wait. I was misinterpreting this territory. Is this even a map? That's not a map. Okay, so we want a map from a coordinate to all the things inside to a list of points. Okay, so we flat map by nearest coordinate, and then we go to list. We don't group by identity. That's silly. Wait, we need to maintain the point actually. So P. Actually, we don't need to keep track of where that point is, do we? Yeah, we do need to keep track of where that point is because we need to check that none of them are on the list. So nearest coordinate P. And then group by, let's make this very explicit. So we have a case point. No. We have a point, and then the coordinate it goes to. And we want to group by the coordinates. And then we're going to do a group map because then we want to take these lists of P and C and just turn them into P. Group map. So again, we have P and C. I'm just returning the P. Oh, right, this is an option. So we're going to map P to that thing. Okay. Um, great, great, great. So now we have a list of territories. Let's check the size of that. So territory dot key set dot size should be chords dot size. Yeah, great, great, great. And then now territory map. Oh yeah, we want to filter out the ones that are infinite. So let's take this thing and make it a function. Def is finite and some collection of points. So we'll call that a territory, just a list of points. It's hard not to do it yourself. Wait, what do you mean? I lately only did so much team leading stuff. I hardly coded something myself, delegating stuff all the time. Yeah, it's hard not to. Yes, I get it. Yeah. Yeah, I feel for you. I wish you had more coding at work. Okay, so territory for all, and then P, we do the same thing. Um, oh, we're still doing that for every point in the territory. There's got to be a more efficient way to check that. I need an efficient way to like take the intersection, see if a set of points intersects an area. Okay, this is a candidate for making more efficient. There's certainly some way. But we can at least filter this. So territory map, filter, great. And then we take the values map size on max and this our ends one. It's natural evolution of software engineers, most end in management. Yeah, I want to avoid that. Like if I climb at a company, I want to end up with more of an architect role. But I kind of also want to build a bit of a consulting career where I'm picking projects. Yeah, some kind of consultant where I can handpick, like high impact projects that are interesting, Okay, it gave me an issue with his empty.max. Okay, so let's do this step by step. After we filter this, what's the size? Oh, so it decided that all of them are finite. Um, we want it to be finite, and it is finite if the inner contains P. Or, hold on. We, yeah. Okay. The bounding, just the edge pieces. You know what? Let's do this. We're not going to do inner and outer. We're going to do, um, we just want to check the edge. I think I tried to check that it's in the inside, but not in the outside. But if it's in the inside, it's also going to be the outside. So I want to check, I think I just want to check that inner contains it. That's sufficient. Oh, okay. There's my alarm. I think that's sufficient. That the inner contains. Oh, 2-minute alarm, everyone. So time to get ready. So this should work. Yeah. I don't know. I might get it right now. If this doesn't work, I'll put it away. If it works, I'll also put it away. 5126. Oh no. Okay, 5126 is wrong. Okay, we can try that again afterwards. Day 06, 2024. I don't have a full script. I do have a file with boilerplate code in it. If I get coffee now, I won't wake up for work tomorrow. I know the feeling. Yeah. I am. You're Pacific. All right. Yeah. Good luck. Good luck to you. 50 seconds left. I'm Eastern. So for me, this starts at midnight. And for blue, it's like 6 a.m. at your time. Alrighty. Early riser. Okay. And it's ready to pull. I will start by looking at the input. Oh, yes, it's a grid problem. Awesome. Okay. We're going to kill it. We're going to kill it. Basics. Guard Gallivant. Historians search for a chief. Unfortunately, a single guard is patrolling this part of the lab. You start by making a map, your puzzle input of the situation. Okay. The map shows the current position of the guard. Okay. Okay. Lab guards follow a very strict patrol protocol. If there's something in front of you, turn right. Otherwise, forward. Okay, okay. Hits an obstacle, turns right. And at some point, what? Wait, how do we know when it ends? Eventually, the guard will leave the mapped area. Okay. Okay. Import is dot point in area. As day 6 not downloaded? Oh, it is not. Yeah, this problem does sound fun. Okay. What do we call this place? Until it leaves. Okay. We'll call this a mapped area. Well, mapped equals area using input. Dot to vector, I guess. Okay. Map up size. And obstacles. There's pools of polymers. I'll call them obstacles. Val obstacles equals mapped that points iterator. Uh, um, okay, and then we'll make that a set. Oh wait, input, or we filter rather. Okay, so we filter for the points such that it's equal to the pound. Just make that a set. Um, oh, wait. Uh, wait, where is my, oh, it's been too long since I've used this. Okay. Um, that's the idea anyway. So we take all the points. I had a method for checking what a point is mapped to. I'm just gonna call this area because I keep thinking of this area. We'll do this val obstacles. At this point, I forgot what my shortcuts were. X from just area dot x range. Okay. If area, then we yield area. Okay, if area p equals that, or rather, I guess we do input p dot y and then p dot x. Okay, then we yield p dot size or obstacles. Okay, lost a little bit of time there. Being silly. Guard. Um, actually, the guard's gonna be a tuple of point and direction. So let's import direction as well. Case class guard, pause point, direction dir. Okay, so we're gonna do area dot points iterator dot find, and is it gonna start north? Let's find a p. Yeah, let's find a p that's not either an obstacle. C is not equal to dot, and C is not equal to that. Dot map case. Yes, it knows what I want to do. Great. Okay, and then we just iterate. Iterator dot iterate. So now the path the guard takes, or whether, yeah, the states to the guard. Wait. Does this work? That doesn't work. Um, yeah, we find a point. Oh, no, no, no. We need to match in the C. Find returns an option. So we're going to do like a dot get on that. And I guess we just define C again. So C match. And then in all these four cases, we replace that with position P. Okay, so this is the initial guard state. Um, yeah, so we have case guard P in a direction. P.move is in fact a method we have. And if next is an obstacle, rather we could just do if obstacles, well, I want obstacles to be a set. Dot to set. Or, you know, we can do this. Set dot from. That's nicer. So we check if the obstacles contain next, in which case we turn. And that's our next state. If obstacle is next, then guard, same position, but the direction not turn right. Else, we return guard in the next position and maintain the same direction. Okay, path dot take while. The position is within our area. So area dot contains g dot pos. Okay, and then the size of that is our answer. Val ends 1. It's not down, left, right. It is north. Yeah. NS, W, and east. And we have other issues. Oh, we want to do a dot get on this. Guard, this would be a guard. Okay, 5578. Okay. Mm-hmm. 5578 didn't work. Let's define a visited. Okay. And then we have the visit that size versus a 5. Oh, wait, that's why is that different? Oh, right. Two set 4883. You have to wait 4 seconds. 1, 2, 3, 4. Okay, okay, there it is. Okay, part 2. And how did I do? 2000. Okay. What's this? So for part 2, while the historians begin working on the guard's patrol route, you borrow their fancy device. Um, they explain that guard's patrol is simply far too large for them to safely search the lab without getting caught. Adding a single new obstruction won't cause a time paradox. Guard will get stuck in a loop, making the lab safe to search. Okay. Fun. I would notice. There are only 6 different positions where a new obstruction. Okay. There are 6 different ways to cause a loop in the first one. Okay. It doesn't really matter how you choose to use an obstacle so long as the historians can put it into position without the guard noticing. How many different positions can you choose? Can I just... Hmm. So we put it somewhere along the guard's path. Can I just iterate over those 4,000? Like, how fast did this run? Like, that would work, and we could just test each of those. Um, def. Okay, so we'll make a new method that walks a guard. So we have a starting state for the guard, and then we have a set of obstacles. And yeah, this is basically the same implementation. So we walk guard around our original set of obstacles. My part 2 code is running terribly. I believe it. This probably needs optimization that I'm not going to put in the first route. F. Hinkle, hi, welcome. Wait, walk shouldn't return a guard. This should return some sort of seek of guard positions. Oh, I guess this returns the next. Okay, hold up. Nope. Okay, so guard walk those obstacles. Okay, so part 1 should still work there. Um, we could try to eliminate candidates from this 4,800. I mean, if we have, I'm not sure how we would eliminate. Like, we could eliminate the ones that just send it. We know would send it outside quickly. You just check that it sends outside quickly. Um, we could optimize a bit of the path instead of. So here, when we're walking it, instead of like generating the next state, we just keep going until we just find the next obstacle in its way altogether. Um, yeah, so this is the old version. It works. Let's make a more efficient version. Um, next obstacle. But then now this would have to return a set of guards. Okay, so that's not a set of points. It would return a line. And then we get a list of lines. Okay, so maybe we won't make that more efficient yet. But the idea is to return a line as well as a new guard position. Okay, so we have a way to make that more efficient if we end up needing it. But the general idea will be to take visit dot map. So we have a new point. And we could do the full walk. This should be a method that generates the path. So guard walk obstacles plus P. And we check if that is infinite. So cycle detection algorithm. Let's put a stub for that. Def is loop path is an iterator of guard. And we will use the tortoise hare method. So we map that to get a path. And then filter not is loop. I guess filter is loop. Dot size. Okay. So that's the right idea. And then now we need to implement the tortoise and hare algorithm. Except a state isn't necessarily if the guard is in the same position facing the same way. So we want to duplicate this path. So path dot duplicate. That's a method, right? Yeah, returns to val. Yeah. T path and H path. And so we move the hair twice, move the T once. Okay, so wow. I guess we can do like this path. You could put a filter on it. Oh, it's already doing the take while. Okay. So while H path has next. T path equals T path dot next. And H path we would do twice. This isn't a good start. I think we should just move. I don't think we move the tortoise here. I think, yeah, if H path has next, at this point, we move the tortoise and the hare. Oh, hold up, hold up. We can't quite do that. We do have to have some point. Okay, so we're going to do an H path dot next. We're going to start with that. Okay, move the T and move the H. And check that those are. And I don't want to break out of the loop and return here. I mean, sure, whatever. I'll take that implementation. I hate doing breaking things with the return like that. Otherwise, false. Oh. And I guess we don't need to take tpath dot next here. Yeah, yeah. I feel like we should construct another. Mm, to be satisfied, I want to make this more functional. It's kind of very mechanical. Okay, but I mean, that should work. It's evaluating. Failed to evaluate, timeout reached. Okay, so we take that line method from above to make this more efficient. Let's comment that out so it doesn't keep running. And we could test this. So is loop, let's say guard. Let's make a list. And we'll let Copilot make a test for us here. Mm-hmm. And let's make this a loop. So 0, 1, and dir.south. So this one's just walking back and forth. And iterator.continually. Then we do our lesson here. And we flatten that. Okay. You got the right answer, but your initial code took so long. I always kind of wonder if I should um, just let a brute force implementation run for a while. And then we flatten this, not flatten. And this should come true. In fact, we could let's do this instead of this list. What is the path? Let's just take this from the problem. Dot take 10. Okay, so this should come out true. Oh. Shutting down the server because it tried to run ans2 for too long. 9 minutes of waiting. Yeah, I think I would. I might run out of memory. Worksheets are nice, but sometimes garbage collection is garbage. Okay, so I know I can make more efficient here. Where's my to-do? Actually, I'm going to close this down for a second. So that it's running again because metals decided to crap. Or I decided to crap metals. Okay, so our more efficient method is going to be here. So I'll take the line that the guard walks. And I don't know, a lot of these paths have kind of the same. What if we memorize this? Right? Like a lot of paths will have commonalities. What if we memorized? Kind of hard to memorize because the list of obstacles changes. If we could easily determine what's like locally not the same. Okay, let's add that to our imports. Swapping X and Y, yeah. You should make a point class. It helps prevent errors like that. Unless you have code like this here. I'm pretty sure I had like helpers for doing this kind of thing, so I never have to reference X and Y because I do that. Okay. I want to look in front of the guard for the next obstacle in there. So we could just search obstacles that have the same. Let's match based on the guard. So guard match. Case. So whatever, there's some pause and dirt on north. If it's north or south, can I do this? Or dirt on south. So it's vertical. I don't know yet. And case west or east. Now we filter from the obstacles for points that are on the same thing. So obstacles dot filter. Actually, we could pre-process obstacles. Well, obstacle vert. So a map from an int to set of points. And we group by X. Yeah. Okay. So we don't even have to filter here anymore. So we have a point. And we just check the one that's nearest and in front of it. So X and Y. So obstacles vert. X, I don't know about that two list thing. I don't like that two list. Um, so these are a set of points, and we want the nearest one. So now I guess we further filter on the direction. Can we do this dir at that? Okay, let's do a match. Dir match. We only care about north or south. And in either case, we're going to do something like this. We're going to take obstacles along the same vertical line. Your part two now takes 8 seconds. Oh, great. Oh, it's a water bottle. Yes, this is a green water bottle. So, yeah, I guess I'm transparent. Let me see. Yep. That's funny. I didn't think about that. Kind of a cool looking effect. You can still kind of see the water in it. Huh. Okay. So we just want the nearest one that's in front of it. Dot, well, we filter the ones that are behind it. Dot filter. Yeah, exactly. And then I don't know why this is necessary. Oh, right. I was generating a line. Uh, yeah. So we don't return to guard. We return to guard with a new position. So with dir dot turn right. Um, so val line is going to be, oops. I'll tell you what I did after you're done. Okay. Is it a fancy trick or is it a trick you feel like you should have thought of? Um, yeah, min by length. Oh, obstacles vert and horizontal are going to be have to be like defined in a closure for each of these, basically. So we can do that in there. Um, yeah. Well, again, we'll pass them in. Okay, we'll pass them in. Okay, so now we return this line. We gotta calculate the end pause. End pause equals. Is it gonna be a line dot start? And does my line dot start? No. I don't have a line dot start. X range dot end. Yeah, so Y range goes from P to Q. So as long as our Q is kind of the end location, point X. Yeah, let's change the order of these. So we start from our initial pause. Um, and we go to pause.copy at y equals p.y. Okay, that is clear. So end pause equals line dot y range. And this is actually this could actually be generic enough. So y range at last dot y. So we have as a copy y equals that. I should just have a way of extracting the last point. So I'll add that to the library. So we have end pause and turn right. And that is where we'll start the next search. So we can get a bunch of lines. Okay. I think that works. And now this filter, I can just change this filter to use obstacle if dir equals dir.north. Then obstacle.y is less than y. Okay. And that works for both north and south. Okay, Blue, good night. Good night. Good to see you. Sun is awake and found the candles. We'll see you tomorrow. Akari Emon, you're still trying to figure out how to a shorter solution for part 2. 4 minutes on a compute cluster. uh, yeah, I didn't even bother trying to run my brute force solution. You don't need to do a Dura match at all. Okay. Length. Okay, surely size is a method. Okay, let's take a look at our line. We don't have a length method. Oops. Class line. Size. I mean, I do have a points iterator. Hmm. That's not quite right. Oh, interesting. Yeah, one of those two is going to be 0. Interesting. Wow, Copilot came through with something interesting. Unless it's diagonal. Okay. I think where I first implemented this, there were also diagonal lines, right? So this list of points could also be diagonal. Um, let's see, let's do this. If horizontal or vertical. Otherwise, we assert. We'll just throw that in, and then we just do dx.abs. Okay, now we don't have to worry about biting ourselves in the future. Larry, New York, rated 12 viewers. Welcome, welcome. Larry, are you the really fast Larry on Midnight Simon's leaderboard? Hey there. Cool to see you're streaming. I'd like to see your AOC solution sometime. So, like a lot of people, I'm trying to make part 2 efficient. Um, and I got excited about this problem when it came out because I already have a little library of point, area, line, direction, all this kind of like grid manipulation stuff. I was just adding size to my little line method that kind of draws a line between 2 points. Um, so I don't have to make any new models. Line.yRange.last. Oh, yeah, here we go. Great. So what I was doing, I was doing a few things to make things more efficient. And one thing I was doing was having a guard find the next obstacle efficiently. So, like for part 1, I basically did a simulation of the guard going through every point. This still follows a simulation idea, but makes it more efficient by not like having the guard move. If we have all of the points that might be on the same column or row indexed already, then that should be a bit faster, right? Like if there are no points in the way. Oh, wait, I have to handle that case where there's no points in the way. Uh, yeah. Okay. Handle case, no points in the way. Then I don't know what we return in this case. But yeah, the guard will go out. Any private leaderboard link? Yes. Bang AOC should do it. There's the code. And there might be more related commands. Nope, I don't have a list of commands. Oh, no, I guess it's there in stream elements for that link. Okay, so first, east or west. Oh, did I? Okay, yeah, we have the north or south case here. Um, we do still have to handle this. So val points in way. And if points are empty, I don't know what to return if points are empty. I mean, I suppose. Yeah, we just take the boundary point. And we make that the end of our line. And then we keep the guard facing in that direction. And then we just have to check that the guard isn't facing outside on each iteration of this walk method. Yeah, absolutely. You should join. Just keep bumping me down lower on that list. Yeah, okay. I don't like this big, long if else thing going on. But I'm pretty sure Copilot's right. I don't like this return either. You don't need to do a return. And we don't turn the guard right, so we just keep the same direction. Okay, so we can check if a guard is out by checking if between two states they're still facing the same direction. Otherwise, now this line becomes points in way. You have to choose one. Oh, points in the way. And that's our end pause. Actually, you know what? We should define our end pause first, rather than defining a line. That's the problem with Copilot. Sometimes they do weird stuff. Oh, we were using the line to check the size. Yeah, whatever. We can refactor that later. Great. So that looks good. And we'll let Copilot implement the other case. Case guard as a horizontal. So pause. Okay, yeah, same code. I am gonna trust that because it should be just copy pasting my north-south solution and changing things. And that should be good. Now, I suppose we could test this method basically by using it in part one. It's so much more involved than the simulation one at a time. What is crit? Thank you for the follow. Okay, just for the people who are new, I'll show my part one approach. Basically, I define my area and gathered the obstacles into a set. And I had this class to hold the guard state, so their current position and the direction that they are facing. And this is all too much code to figure out the initial location of the guard. In fact, I should rename this because it could clash with other things. Rename symbol init guard. Okay. We don't want to accidentally use that when we want to use a generic guard. And I defined this walk to simulate a guard's next position. Right? You basically check if the next position is an obstacle. And so you just turn right, and otherwise you keep moving forward. And you can do a path by just calling iterator.iterate with this. This is our initial state, and we use a walk method. And yeah, that got us ends 1, no problem. Is it always looking north? Okay, that'd be convenient. I'll do that in my refactor. And for part 2, I implemented this is loop method, which I don't think I've tested. Has this worked? In fact, I haven't seen this compiling in a while. Okay, yeah, it decided that that's a loop. I'm gonna trust that my is loop is fine. It's like a tortoise hare method. I don't like this code. I will rewrite that, try to make it nicer later. But yeah, now that gets used kind of here. So the path we kind of generate differently now. So let's define a method that gives us a line path. Line path for guard and a set of obstacles. And iterator of line. Do I want an iterator of line? I think a seek of line will suffice. Yeah, the next obstacle in line of sight. I mean, for part 1, I did walk step by step. I'm finding the next obstacle by line of sight, and I'm trying to optimize that by kind of pre-computing for each column, like what are the set of points in that column. So this should be like a small set of points to check. I think that's better than just iterating over the points that are in front of the guard. I'm not sure. It really depends on the input. But for a lot of things, that should just be empty. Or, I mean, honestly, just a set of 1 point. I think this is a point at which I should step back for a second. I spent a lot of time optimizing, and during that time, a lot of other people have been able to figure out how to optimize theirs. So maybe I am missing something that I could have done. Is there a faster way to figure out? Maybe instead of checking a point and checking if turning into an obstacle will make a loop, which I guess this grid is very sparse. Well, no, so I was still doing this on points that are along the path. So I could check every point along that path, but what if I could find some other way without checking every individual point? Let's take a look at how sparse these were. I mean, yeah, that's pretty sparse. There's like 5 in each. I feel like hidden in here somewhere is like some way to memorize a lot of this. Because a lot of right? Between each of these runs, most of the map is the same, right? If I decide to put this one here, then a guard who's here is going to do the same thing every other guard in almost every other like position for this would do. So maybe I could memorize a walk method for a point and its vertical and horizontal lines. Right, and in a lot of cases, that will just be the same old. So there's a thought. There's a thought. Um, I could try that if this doesn't make it efficient enough. I'll think about it. So potentially memorize, potentially what else? I mean, if we know the kinds of path the guard could take, we could prioritize. I don't know. I don't know. We'll just continue on with making the simulation approach more efficient. And if this iteration doesn't work, I do have that memoizing technique to try. Okay. So line path, a sequence of lines. So iterate guard walk with a set of obstacles. Well, we don't want that walk. We need to define horizontal and vertical and pass those in. And it will always be based on this one here. So val hors. Okay. So vert hors. And we will pass those in to this walk method. And I guess the lines. Well, we can do the take while here. So we take while. Guard, the area in front of the guard is. I suppose we should put the guard out. Well, okay, so we have a line. Oh, well, we have a line and a guard, right? Walk returns us a line and a guard. So take while, case, guard, position. Area contains that position. I think we want the inner area. Well, So this ends when the guard is on a boundary point facing outside. We could just enumerate those 4 cases, but I feel like there's a nicer way to do this. I can't think right now. We will just enumerate. So we'll do a Durer match. And we don't want all those cases. I want like my exhaustive match. Here we go. Whoop. Okay, so area dot top border contains pause. Oh, hold on. Doesn't contain pause. So we take as long as the top border doesn't contain our position. Great. Right border. Why would you go to right border there? Oh, wait, because I'm being silly. This should be if we're facing north. North, south, east, west. Easier to think about that way. Okay. Okay, so we take, well, it's not ended. Oh, but we're going to miss that last one, aren't we, if we do it that way? I think we should just continue to iterate and have the guard walk outside. So what do we do when there are no points in the way? If there are no points in the way, we put it on the boundary, right? Well, if we put it outside of the boundary, if we put it outside of the boundary, then we still want that point in the path. But the thing is, we can keep iterating. And when it appears and it's on the boundary and it's walking outside, when the guard is on the boundary and about to walk outside, then we just put the guard outside. And then that's the one that we can drop. Okay. We'll just put those cases here. Guard, pause, north. If pause, if area dot top border contains pause, then line from pause to pause at move dir, and pause up dir. So the guard just walks outside one step. Okay. So we'll catch those cases, and writing code like this is great because Copilot can autocomplete that. I am bracing AI. Okay, then now here in our check, take while area contains pause. That should suffice. Now we know when the guard has left. Yeah, this is the lines of the path the guard is taking. And do we want to seek a line? We can figure out what to do with that later. A list of line. Great. Now we can take the visited from part 1. And for everything along that path, we replace it with an obstacle. Visit is a set. we're going to subtract the one that the guard starts on minus init guard dot pos. And the one the guard's looking at minus init guard. Or no, that's valid. That's valid. We're not going to remove that. Okay, so we take that position and then we have the guard. We get the line path for that position. Map line path. Oh wait, not quite just that. So we have a new set of obstacles. Line path guard. Just init guard is fine. Obstacles plus P. Okay. And then we check if things are a loop. Oh, you know what? Why did I write an is loop method? We can just check if it leaves. Oh, wait, no. We do need to check. Yeah, we do need to have a way of checking that. So a loop. We could have a quick version that basically just checks the size of that. And we don't really care about the size of the loops themselves, just the number of loops. So this was our isLoop method from earlier, iterator of guard states. We're not going to use that because we don't have an iteration of guard states well, we kind of still do, even though we're not doing every step the guard takes. A loop would be from those. Okay. So dot filter line path, or I don't know, lines. And then lines dot map guard. What is this a list of line? Oh yeah. So we did this walk, and this gives us a guard. This is the wrong walk method. Def walk. It should be using this method. So it returns a line and a guard. Okay. A line and a guard. Larry, you're going to sleep? Okay, well, GG. Well played. Thanks for stopping by, and thank you again for the raid. Okay, so iterate would normally take something that goes from a guard to a guard. But I don't think that's what we want here. We're getting a list of line, strings a line and a guard. We do want to keep those lines with us as well. Actually, we don't. We don't care. We just care about the guard states. Yeah, that's right. So for this walk, we don't even need the line of positions the guard occupied, do we? Because we're not counting those anymore, not for part 2. So that's why I added those initially. But yeah, we can remove that. So that 2 to take the guard. And we take while, so at this point it's just a guard. Area that contains that position. Um, take while the guard is in bounds. And then, oh, that take while could be problematic. We need to do a filter first. Filter. We need to make sure it's not a. Well, actually, this is fine. So valid card states. And then, oh, line path is returning the lines. You're just returning a list of guards now. Yeah, we don't care about. We'll continue to call it line path for this time being. So for ends 2, we check. So for every point in the original guard's path, we do the line path for that initial guard with a new set of obstacles. And we want to filter these for things that are not is loop and not size. And since is loop works on an iterator of a guard, so guard states g.iterator. Okay. Okay. And if at any point this just runs out, then it returns false, right? Cool. I don't know what this code is. We filter that out. And there are still ways to optimize this. Oh, is there a problem here? Okay, there things are not found. Case guard pause. Contains is not a member of line. We should just implement it already. So line def contains point, and this only works for horizontal. That doesn't exist. So horizontal, then x range contains p.x. That's a vertical. Otherwise, it's diagonal, and I'm not going to check that implementation. Okay, there we go. We should give her an assignment here. Great. Now, other problems? Valid guard states. This is simply returned. Okay, we keep doing the walking, and we walk to the next line of sight obstacle. Guard position. Yeah, we take while the guard is still in bounds. So that iterator will stop at some point. And let's just make this an iterator. This this now means line of sight path for the guard. It's not a list of lines. So don't even need to call that iterator anymore there. So we just filter is loop. Okay, here's a moment of truth. 0. Okay. So now, apparently it thinks none of them are loops. But it got through all of them pretty quickly. Let's see what some of these look like. So, and how fast did that run? Output, that ran in 3 seconds. Okay. So if that's good, that's good. Just so we have a set of iterate. Oh, set. Why are we calling map on a set? I really need to have a linter that prevents me from calling map on a set. That might have been why. Hmm. That might have been why an early implementation was too slow. Okay, so a list of iterators. What's the size of that? Yeah, checks out. 4,000 iterators. And apparently thinks all those end. So map dot take 10 dot to list dot size. Okay, so all of those have at least 10 elements. Let's take there are a bunch of them that end at 7. Whoa. Are all of those identical? Okay. So val p's, it's called. So val p1 equals p's dot next. Val p2 equals so p1 dot to list and p2 dot to list. Oh, right. This is a list. So just p0, p's, yeah, p0 dot to list and p's 1 dot to list. I have a sneaking suspicion they're identical. And we can just do that same elements as p's 1. True. Okay. Well, visited minus init. I mean, all these p's should be distinct. So line path might not be using. No. I'm just going to rename that symbol so I know I'm not shadowing. And let's check our walk method. Make sure it's not using obstacles. Okay. Let's delete these two. Make sure that those aren't being used somewhere. Um, yeah, we're just discarding that. That's fine. They all end after 72 segments of the guard's path. I mean, each of these should be working with a unique set of obstacles, right? I mean, like this here is a unique set of sets or of points. Yeah. And then each of those are added or yeah, added to the original obstacles list. Okay. Then why is line path generating the same path for all of these? Let's just make sure. In fact, we can just take all of these p's.map dot to list dot distinct dot size. Yeah, there's only one path ever being taken. But at least it's snappy. At least it's snappy. That's a good sign. Okay, I'm just gonna rename my original obstacles, file obstacles. I'm gonna make it really long so it's obvious if it's reused somewhere. Name symbol. Okay, great. Great, it's supposed to be used there. So let's just backtrack from our ands to, yeah, we add p to that. IsLoop, my isLoop method doesn't even use obstacles. Cool, cool. And importantly, this walk method does contain unique vertical and horizontal maps. Okay, well, let's inspect one of these paths. Is one of these paths like sane? Just do it for a normal set. So we'll undo that rename. That should have been our first sanity check, actually. I mentioned it earlier. Run this on part 1. So line path for init guard and for just obstacles. Okay. Interesting. So 5971 north, 5970 north. Okay, there's just a bug in this somewhere. 5969 north. It's kind of like moving backwards. It must be some place where we're using. Okay. Well, I know where the bug is. It's somewhere in here. So if points are in the way, we're not getting here yet. So this is where we create the line. We check the points that are in the way. And for each of those, we make a line from pause to pause.copy. And we take mint by size. What's the size of a line? Do I actually have a size method in my line class? Oh yeah, yeah, I defined that earlier today. Okay, so we make a line from our position to a, a candidate end positions. Val candidate ends. We'll just define this differently. In fact, maybe in rewriting it, we just won't rewrite a bug. So, oh, wait, we already have a list of points in the way. Yeah, points in the way is our candidate ends. Let's do it differently then. So points in way dot min by distance to a start pause. Pause dot dist. Yeah. Val end pause. And now our line is just line from pause to end pause. That's a nicer definition anyway, and maybe it doesn't have a bug. Oh, excuse me. Okay, and the same code works right here. And now let's see if this changes anything. Give a sec to run. So that hasn't changed anything. That's not where the bug is. It's walking backwards. So in our example path here, so that's the initial location. So we need to look at how we're calculating the end position, which we did just look at. I should break this down into smaller things I can test. Let's just test our walk method. So let's walk our guard, init guard from the obstacles. From these obstacles. And let's see where that first line goes. And we can compare that against the input. Just look at it visually. Okay, so align 5971 to 5970. So if there's, oh, wait, if there's an obstacle right in the way, size method might be wrong. Let's see, line point, let's find a point, P, yeah, 0.00 is fine. So line from P to P.move north, that size, this should be 2. And if we move 1, 2, 3, 4, if we move 5 times, then it should be 6 because there are 6 positions in total. So so if you move 6 times, that should be 7. But also maybe that's valid. Let me look at this here, how we're using it. So end position. I mean, are we even using size here? These are candidate end positions. Yeah, I don't know why I tested that. We're not even using it. Okay, back to this method here. Um, let's just look at the vertical case. Our first one's vertical. This might be wrong. If direction is north, our north basically means move up. Yeah, okay, our y is kind of inverted. Y increasing means south. Okay, so yeah. So it is in a way if y is oh wait, no, it was initially less than the obstacle that y would be less than because it's above. Okay. Hmm. Oh, hey, thank you for the catch. Um, great. So I think we made progress here. It turns out my contains method was wrong, the one I implemented earlier today. It's easy to assume that that's correct because it's a library method, which are normally tested, but it's a library method I added just now. So now that won't be caught too early. Great. So let's look at some of our other tests. Let's see. I mean, now we have some other issue happen. Oh, no. This is good. We're seeing some variation. Let's just straight up uncomment our ends to code. Okay. Every path is still the same. So that is still not good. And interestingly. Okay, I'm gonna delete some of this clutter that we have here. So we're still using that is loop. I'm confident that the is loop works. So line path. This is a line of sight guard path. Guard corners, we could call it. I'm not sure. Um, that doesn't matter. This doesn't matter. Let's give this bit a name here. Um, val. Yeah. Well, no, that's fine. So visit my snake guard to list, and then we map each of those to a line path. And we should take a look at some of those. And we are taking a look at some of those. Here are the P's. There are 87 different paths, so that's good. How are we turning each of those into a list? Some of these are empty. Why are some of those empty? That's fascinating. Okay, well, that's something to work. Why are some of those so small, actually? So let's compute a line path for something. So let's do line path for the original bit. So line path. Oh, we've already done that here for the initial guard. So 5971 north. And then we're at 5936. That looks good. Facing east. Okay, like that's the full path of the guard. So why are some of those paths empty? I think we're determining. Oh, those empty paths. Those empty paths are all like they started on the border. Must be. No, I mean, even in those cases, it should have the original location of the guard. The guard doesn't move around. Hmm. Okay, well, let's look at the one. Oh, these competent things I was looking at earlier from a print line from earlier. So those are the points in the way. We don't need that comment to help us anymore. So let's look at all of these paths. P's. Dot map dot to list for each print line. And we only have 87 distinct paths. Well, okay, I think part of the problem, okay, well, 1 second. Let's try to find those ones that ended up in 0. So, like, some of these line paths should have been infinite. So it should be invalid to, right? Like, this should be erroring out for me. But instead, we get a bunch that are size 10, which I guess is the standard, like, original path. Some of them size 26, etc. Let's take this and sort it by size. That's sorted dot first. See what some of the largest are. Like the infinite one should show up as 500. 49. So we don't seem to have infinite paths. We seem to be failing to generate infinite paths. And it is getting late. I'm starting to hit my limit. I feel so close, but I might have to. Okay. Well, this is a good run in 10 minutes. What can we do? Let's take a step back. Um, so we are generating a bunch of line paths, and I suspect that these line paths are wrong because none of them seem to have infinite loops. We can go back to the input or to the example data and check one of these that should end up in a loop. That's probably our best bet, to be honest, to catch what's wrong here. These are the kinds of things that will fail horribly once they have actual loops in here. Like this should still end up at 0 because none of those are actually loops. Let's try it out with the example. And I feel like we're so close, it's probably a tiny bug that the example will help us find. On day 6. A-06.text. Okay, we'll save this as example. And we test on the example. Here's our example. Okay. And what can we do with this example? So we could check the line path. Well, we can walk around an example. So the init guard, the first thing it does is walk nearly to the border. Oh, we haven't changed the input yet. Here we go, -x. Okay, so we have the init guard walk. I'm just gonna move this down with the other tests so we can kind of test. Easier to find. Okay, So it walks. Then we have a line from 4, 6 to 4, 0. Why is it all the way at 4, 0? It shouldn't be at 4, 0. I see what's going on. We are walking into the obstacle instead of one short of it. Okay. That's it. That's it right there. So, um, yeah, we have points in the way, min by pos at dist. The end pos isn't quite that. That move, and we take the direction, not reverse. Yeah. Or actually, that should just be defined here. Points in the way that min by pos at dist. Move in direction, not reverse. And then that's our actual end pos, and then direction, not turn right. Okay. And hey, that failing feels like a good sign. This feeling kind of feels like a good sign. Key not found 2. Why are you even doing keys? Oh, okay. The horizontal and vertical. Val, hors. Oh, wait, just where do we define these? Okay, so these need a default value. That with default value set.empty. Great. Okay, and that's still not quite there, but let's look at this new path. So it starts at 4, 6. It goes to 4, 1, and it's pointing east. Okay, yeah, guard is at 4, 1, pointing east. Okay, now let's look at a whole path there. So line path for the init guard with just the normal obstacles. And then we'll just print each of those for each print line. Okay, 4, 6 facing north, 4, 1 facing east. Good. And then 9, 1 facing south. Yeah. So it walked past an obstacle. Wait, 4, 1 facing east. Wait, how did it move to? Yeah, that moved east to 9, 1. And then it ends up moving out of bounds at 9, 9 facing south. Okay, I think we're on this. I'm going to take a quick bathroom break, and I think when I get back, we should be able to solve this. Okay, here we go. 9-1 facing south. And the very last thing we had is 9-9 facing south. And let's look at the grid, the area size. Area that size 100. Right, so that very last one, 9-9 facing south, is the guard sitting on the border. Okay, so that looks valid. Now let's look at part 2 where we place something in the way. Option 1, put a printing press next to the guard's starting position. Oh, hold on. We had the same problem with east and west. So, right, that path we were just showing on screen isn't correct because it shouldn't be exiting. Right, it shouldn't be walking past that. It should be bumping. Okay. So it's the same bug, but for the east and west. And pause. And you know what? I'm pretty sure this can be made generic for both north, south, and east, west. That way I'm not fixing a bug in just one place. So end pause dot move direction dot reverse. All right, let's look at this path. That looks more like it. It was pretty long. Okay. And now we can take this. Yeah, let's take a line path for obstacles plus, was we put one next to the guard on the left. So plus init guard dot pause dot west. I think I have a left, L for left, too. And now we need to take a few. Let's just take 30. And we have a loop. Okay, we have a loop. That's it. We got it. Hey, we did it in 10 minutes. I mean, we did this part in 10 minutes from when I said I would leave if I couldn't do it in 10 minutes. I think it's good to take a step back and think about trying to fix this efficiently. I should have done that an hour ago. 6, answer 6, great. And you know what? Solutions efficient. 1655. If this isn't it, I'm gonna cry myself to sleep. Yes, okay, got it. Okay, great. I know this took me a while, but I'm happy with the models. I know this whole thing can be made a lot shorter. And I know, like we didn't need this line bit. So in fact, a lot of this can be simplified. But I like the general algorithm. That was snappy. Ran in 3 seconds. Cool. So optimizing this was as simple as like I can still do the simulation approach, but you just look ahead, line of sight for the next point. And rather than simulating each step, you simulate just the corners. Yeah. Okay. I think I will start tomorrow's session. I usually log on like half an hour early. I'll start tomorrow's section by refactoring this and making it nice. So that could serve as a bit of review. Let's take a look at some leaderboards. So I know yes, I dropped all the way to 7,000 for that one. I probably dropped some spots in leaderboards. Okay, but I want to see the deltas. Put myself behind here. For day 6, I went from 7th place to 15th place with an hour 45 delta. Crazy, crazy. I wonder where like 8th place would have gone. Okay. So it seems like most people had 1530 delta. This is definitely so an advantage of like recording all of my sessions here is I can go back through and like review my problem solving process. So this will be a candidate for looking over and why did it take me so long to debug that? And how can I avoid that in the future? So that I'll be doing. And maybe in the distant future, that turns into a YouTube video where I analyze all the mistakes I've made, or, just my learnings from all the mistakes I've made. So I think there's a silver lining to having mistakes caught on camera. And that is, I can analyze. Oh, I was the first to finish on the Scala leaderboard tonight, but then I dropped behind everyone. How did you navigate to deltas? Oh, so I have 2 plugins installed, and they are somewhere in my about page on Twitch. You can see them there. But basically, if you search on the add-ons for admin to code, it's at the bottom for me. Yeah, so the deltas are right here, and this is all the graphs. So I have 2 different plugins trying to do stuff. I want to look at my. Okay, so this is my leaderboard here that I have on stream. Based on total score. So I'm still kind of stable there in about 5th place. Here's my score per day. I've had some bad days. Mm. Yeah, I like this plugin. It's fun for some after analysis. And the global leaderboard. I'm not gonna bother looking at that one. Okay. Well, I think it's time we find someone to raid. Give me a second here. Who is still doing enough code? Mike BC Gamer's playing. I've seen them around. Oh, let's meet that. Okay, so let's go see what's going on here. And feigned interest. I haven't heard. We'll visit Michael Peaceful Gamer. All right, continuing the party. Zombie, how did you do tonight, by the way? I forgot to ask. It's good to see you. I assume you finished because I'm seeing you here and not in the list. All right, let's continue tonight over at Michael PC Gamers.